Hi everyone, we are from the CFUTM team. The case study I would like to share with you is a green steam cracking furnace, hydrogen versus electricity. I'm Nabilla, together with my teammates Ayman, Suphaklit, Souleymane, and Naash, are chemical engineering undergraduate Universiti Teknologi Malaysia, and our advisor is Dr. Dinie bin Muhammad. This is the table of content of this video. Start from problem background, best case, electricity, hydrogen, and conclusion.
Naphtha thermal cracking process. This process is considered as energy intensive. For instance, in the case of ethylene production, around 40 gigajoules of heat per ton of ethylene is required. This process has also an environmental impact. For the same case of ethylene, significant formation of coke and nitrogen oxide were observed, and around 1.8 to 2 kg of carbon dioxide were released. The chemical industry is considered as the third largest CO2 emitter. Source and capacity. According to International Energy Agency 2018, the chemical sector emitted around 1.5 gigatons of CO2, which is 18% of the total industrial CO2 emission. And the primary source of this CO2, which is syngas from a fossil fuel.
Our objectives are to develop eco-friendly feedstocks, focus on researching and creating sustainable, renewable, and environmentally friendly raw materials to replace fossil fuels in petrochemical production. 2 is to implement energy efficient processes and adopt innovative technologies and practices that reduce energy consumption and greenhouse gas emissions during petrochemical manufacturing. 3 is to foster circular economy integration and embrace a circular economy approach that promotes recycling, reusing, and repurposing of waste materials and byproducts, reducing waste and enhancing resource efficiency in the petrochemical industry.
Now I will be giving a brief details of the process. This is the process flow diagram of the entire process of naphtha steam cracking. The red box represents the part where we will consider for this project, which is the furnace, which houses the plug flow reactor inside. The cracked gases coming out from the furnace undergoes heat exchange through transfer line exchanger, which recovers heat from the cracked gases to produce steam. The steam from this transfer line exchanger is then utilized as a diluent in the furnace. The cracked gases then go through a series of separation processes to separate the cracked gases into its categories. However, these separation processes will not be considered in this project. The steam cracking of naphtha starts with a stream of naphtha being preheated to around 600 degrees Celsius at around 3 bars, before getting mixed with another stream of dilution steam at the same temperature and pressure. The mixed streams passes through a hotter section of the furnace in a plug flow reactor packed with catalysts to thermally decompose the naphtha into light olefins and paraffins. The transfer line exchanger is employed at the furnace exit to recover heat from the cracked gases to produce steam for the process. Furthermore, it is also required to produce additionally 14.4 tons of high pressure steam at 12 megapascals to cater for an adjacent process. Moving on to the process simulation using aspirin HYSYS, the naphtha feed composition was given in terms of weight percentages of normal paraffins, isoparaffins, olefins, naphthenes, and aromatics. The compositions were used to estimate the average carbon number of the naphtha feed using the hydrogen to carbon ratio, which is 2.2. It was then found that the average number of carbon is 7 in the naphtha feed. The selected compounds to represent the naphtha feed are therefore propane, butane, and then for the N-paraffin, N-heptane, and for the isoparaffin, methylhexane, for the naphthenes, methylcyclohexane, and lastly, for the aromatics, toluene represents the aromatics. The reaction kinetics from the literature review are represented in the table as shown, where the only decomposition reactions were considered while side reactions were neglected. The reactions were assumed to run completely with 100% conversion. The process flow diagram from our simulation shows the naphtha feed being fed up at ambient temperature before getting heated up to 600 degrees. The naphtha vapor stream is then mixed with the dilution steam before going through the plug flow reactor. All the heating and evaporation of the naphtha feed was done inside the same furnace at a higher position, while the reactor is placed nearer to the combustion chamber to achieve higher temperature. The assumptions were made to simplify the simulation where 100% conversion was achieved. The cracked gases supply heat to produce steam from a feed water of 80 degrees Celsius, and the fluid package used in the simulation was the Lee-Kessler-Plucker package. The product stream composition on a dry basis is shown in the table, where the ethylene yield approximately is 30 to 40% of the total mass. Around 10 to 20% also gets converted to light natural gases such as methane, and it was also found that normal paraffins will contribute to higher yields of ethylene. Now I'll be presenting about the base case, which is the natural gas-fired furnace. The energy requirements that was calculated from the simulation was found to be 88.8 gigajoules per hour of operation. However, to approach the problem more realistically, a usual energy requirement is used to account for the energy losses, where 225 gigajoules per hour is required for the process, and 44.6 gigajoules per hour is required for the steam production for an adjacent process. The generalized heat demand of the process and steam production was used to estimate the natural gas requirements. The temperature of the stack is assumed to be 205 degrees Celsius and a dry oxygen content of around 5.8% for the estimation of stack loss. It was estimated that around 7 tons of natural gas per hour is used, and 19 tons of CO2 will be released directly from the combustion of the natural gas per hour.
Hello everyone, my name is Ayman and I will be explaining about electrical furnace heating case. The technology used to provide both electrical demand for the electric furnace and steam demand for the naphtha cracking process is combined heat and power generation, or cogeneration. In cogeneration, the steam drives the shafts of turbine to generate electricity, while it can also be used to heat some equipments in the process or also for naphtha cracking demand. And also, to generate the steam, we only use waste gas from the naphtha cracking, which is methane, and biogas. And lastly, we are recycling back the water or the steam after condensing back into the boiler feed water. So here's the process flow diagram for the cogeneration system. The first thing to design a cogeneration is to get the amount of steam to be produced by the boiler, which accounts for the amount of steam to drive the turbine shafts and generate 225 gigajoules per hour. We get that and multiply it by the enthalpy of steam, and then we divide it by the isentropic enthalpy of turbine. And along that, we add the amount of steam demand for the naphtha cracking, and we multiply it by the enthalpy of steam as well. We get a total of 85.9 tons per hour to be generated. Also, here's some process specification for the combined heat and power, like the boiler efficiency, the efficiency of electric coil heating, the isentropic turbine efficiency, also the steam generated, the enthalpy of that steam, and the enthalpy of boiler feed water. And also we have for the boiler fuel, the mass of recycled methane from the naphtha cracking, around 1.8 ton per hour, the higher heating value, and the higher heating value of biomethane, which is only 90% methane and 10% CO2 and other traces of gases. And from the equation of boiler efficiency, we can calculate or obtain the amount of biomethane needed for this boiler. And as you can see here in our process flow diagram, the high pressure steam is generated and some of that steam is withdrawn to the naphtha cracking reaction or process. The rest goes into the turbine to drive the shafts and generate the electricity needed for the electric furnace. After that, the saturated steam out of turbine goes into the condenser, cooled down by cooling water, and after that is fed to an economizer along with makeup water to make up for the steam withdrawn to the naphtha cracking process. Here, the purpose of economizer is to raise the temperature of boiler feed water by utilizing the waste heat from the flue gas of boiler and increase overall boiler efficiency. After that, we have here carbon capture to capture the carbon from the boiler flue gas using solvent A and B. And that's it for the process flow diagram. Lastly, the innovation of this process is first by the usage of waste gas from the naphtha cracking. We can save the energy consumption by 100 gigajoule per hour approximately. And we only use renewable fuel, which is biomethane, which contribute to SDG number 7, affordable and clean energy. And also by the usage of cogeneration and utilizing the waste heat from each process, the efficiency increases to 86%, which contribute to SDG number 12, responsible consumption and generation. And lastly, by using carbon capture unit and recycling boiler feed water to reduce external water consumption by 85%, we contribute to both SDG number 13 and number 6. And that's all.
Hydrogen can be used as a fuel in heating the furnace. One of the alternatives in producing hydrogen is through electrolysis. This process splits water into hydrogen and oxygen. The electrolysis reaction, which is H2O, which splits into hydrogen and oxygen. The advantages of electrolysis for hydrogen production: the first one, which is carbon-free, no carbon dioxide or greenhouse gas emission associated with this process. Secondly, renewable integration. This can be linked directly to renewable energy sources. Thirdly, energy storage. Hydrogen can be stored and used as backup or during peak demand. Here is the overall process flow diagram. As can be seen, the electricity and water are passed through the electrolyzer unit, where electrolysis takes place. And out of the electrolyzer, which is the hydrogen and oxygen produced, the hydrogen produced, which is then further supplied as a fuel for heating purposes. According to our calculation, based on the energy demand, the input energy into the electrolysis process, which is found to be around 337,000 megajoules per hour, and the energy content of the produced hydrogen, which is around 270,000 megajoules per hour. From there, the efficiency is calculated, which is around 80%. And CO2 emission is 0. Based on the equation, as can be seen, only hydrogen and oxygen is produced, which makes this process very clean and carbon-free.
Hydrogen production from steam rewarming (SMR) is one of the most widely used and economically methods. SMR involves the reaction of methane with steam over a catalyst to produce the hydrogen gas that we use in the furnace. The process typically takes place at elevated temperature, and it is a highly endothermic, meaning it requires a significant amount of heat input to drive the reaction. The key point about the hydrogen production from SMR are feedstock, head temperature and pressure, catalyst, hydrogen purity, and CO2 emission. Here the process flow diagram of SMR and CCS. You can see in the slide there are feedstock preparation, feed purification, steam rewarming, water gas sieve, CO2 removal. CO2 removal units such as a pressure swing absorption, PCA, a system or membrane separator can be used to capture the carbon dioxide and produce a high purity hydrogen stream. The next is a methanation. Step may be included to convert any remaining carbon monoxide and carbon dioxide to methane. This step can be improved the overall hydrogen purity. The final step involves the purification of hydrogen to remove any remaining impurities. Simulation SMR using Aspen hazes. The fluid package I use is a Robinson. From that simulation, that we conclude that the efficiency is around 80% and the energy content is around 159 megajoule per hour.
In conclusion, we can see that both electrical furnace and hydrogen-fired furnace has overall higher efficiency than the conventional heating for naphtha cracking. However, for electrical furnace, it uses the least amount of energy, while for hydrogen furnace, it emits or store the least amount of CO2. And compared to electrical furnace uses renewable energy and recycling water. However, for hydrogen furnace, it uses renewable energy as well as clean energy. And that's it for our group. Thank you so much.